Hi, I'm Albaugh, and I'm presenting work done with Scott Hudson and Lenning Yao on augmenting a manual knitting machine to make it a system for interactive fabrication. Within computational fabrication work, we've increasingly seen systems which allow for real-time control or collaboration between a human user and fabrication devices like 3D printers, mills, and laser cutters. Interactive fabrication systems often give the user the ability to reason about their output directly in physical space, and the immediacy of these systems can support impromptu and improvisational creativity. It's worth noting that many of these works involve sophisticated hardware equipment to mediate between the user's input and computationally controlled output. Switching gears, knitting is a way of making a fabric out of a grid of loops of yarn. Knitting can be done by hand on the pointy long needles, or it can be done by machine, in which case each of the columns of loops is held at the top by a hook-shaped needle, and new stitches are added at the top. The needles themselves are arranged into a row called a bed, and on the kind of machine I'm talking about today, there are two beds facing each other. Even within this kind of machine, there's a wide range of types. A lot of the contemporary research in machine knitting, and indeed most of my own research, is done on the very fancy machines that are fully computationally automatic, like the SIGCHI glove knitting machine that we have in the textiles lab. This kind of machine can knit complex shapes with no user intervention at the time of knitting. I'm sure you're not surprised to hear these can be very expensive. But there's a similar kind of machine that's not electronic or even electrical, it's purely mechanical. A human stands in front of this machine and uses their human arms to operate it. This kind of manual knitting machine is very well established. It's been essentially identical for over 100 years. But they aren't just crusty antiques. This very same kind of machine is tremendously popular in textiles design and engineering school, as well as for serious hobbyists. We see this as an opportunity. This is a very cool machine that's appreciably more financially accessible than an automated industrial one, and it even has some capabilities of its own. However, to operate this thing, a person needs to pull the carriage, highlighted in green, back and forth across the machine. The carriage contains the cams that are what pushes each needle up and down to do the knitting process. This part requires a bit of upper arm strength, but it's honestly pretty fun. If you just want to make one big rectangle with every row the same, you are golden. The challenge is when you want to do something more complex. So first of all, you might notice that unlike in the renderings I showed you before, the needle beds on an actual knitting machine are made of opaque metal, so you can't really see much of the in-progress knitting, just the top row, sort of. So problem one is that the user has no real cues about the recent past state of the machine. Now here's a view of the front carriage. You see it's got a bunch of levers and settings, and they're barely labeled. It's confusing, intimidating, and on top of that, the needles in the machine come in two flavors, one with higher tabs and one with lower tabs. And I know it looks subtle in the slide, but it is a little bit easier to see when they're installed on the machine. These tabs are how the carriage grabs each needle to actuate it. So back to looking at the carriage, there are two sets of levers here on the front carriage, mirroring each other, corresponding to what should happen when the carriage is pulled left to right versus right to left, and then there's a matching set on the back bed for each direction as well. Within each bed direction set, there's two levers, each with 3 positions. The combination of these lever settings determines which of the higher low needles gets grabbed and how, and you do not need to remember this. I'm mostly telling you this to make a point that there's a lot and it's actually hard to remember. And in addition, there is another setting. You can move the back bed laterally relative to the front. This is called racking. It also affects the patterning. So in this swatch, the wiggly bit in the middle is entirely about changes in racking. It's not carriage settings. So all of this together, it's a lot to keep track of, meaning that problem number 2 is that the user is likely to have a hard time reasoning about the current state of the machine, what the levers mean, how they're going to interact to produce the next line of knitting, and therefore they probably have only a tentative grasp on possible futures. But tracking state and drawing inferences are things a computer should be good at. So what if we add those capabilities with computers directly on top of the existing machine? Tracking state means sensing. So we attached an accelerometer on the lever that controls rack, and Hall effect sensors at the left and right side of the machines to detect when the carriage completes a pass. The most complicated thing to track is the carriage settings because there's so many of them, so we do that with webcams as sensors. We mounted 2 webcams up on the bow of the carriage, one pointing toward the front, one pointing toward the back, and the feeds from these 2 cameras are split into 4 crop zones, one for each of the bed directions, and we trained a simple image classifier to recognize each of the setting states. So putting this all together, we have a couple different kinds of sensing being piped through a server, which receives sensor events and image data. And from there, we maintain a machine state via a model, which is specific to the way the carriage settings work on this kind of machine, but it's built on top of a general purpose knitting machine model. As an aside, because the system has a general knitting machine model at its core, it's possible to record operations on the manual knitting machine and play them back on the automatic one. And in this case, the automatic machine happens to have a smaller stitch size, so the duplicates are smaller. The final layer is a set of interaction modules for various contexts. I will show you 3 in this talk. So, putting it all together, we have a system that can record the machine's past and current state and make inferences and give advice about the machine's future. The main thing that's different from the user perspective, of course, is the computer screen. In the most basic module, the screen shows the user an interpreted view of carriage settings. So the next direction, leftward or rightward, is highlighted, and text labels confirm which of the 3 positions each lever is in. On the right, the diagram of the needle bed is notated with each needle's role in the current settings, and a diagrammatic mass spring simulation keeps up with the knitting as it's done. The portion shown in the yarns color, so burgundy here, is already knit, and the ones highlighted in yellow show what would happen if 2 passes were knit at the current cam lever settings. This is a sort of a little mini preview, and it can highlight possible errors, such as, in this case, too many loops accumulating on the needles. In this screenshot, you can also see how the mass spring model highlights the wavy patterning that comes out of racking alignment changes during knitting. This kind of patterning is particularly well suited to this machine since it only involves changing one lever. It is, however, possible to do more complex patterning on these machines. For example, this armband has a section of knitting where 2 separate layers form a pocket. Perhaps you might like to use a pocket structure like this to embed electronics into your knitting. Unfortunately, this pattern will require you to change lever settings every other row in a way that is not fun to keep track of. So in the second module, which is an assistant for pocket knitting, we show the user a stream of instructions. Any changes they currently have to make to the machine settings are highlighted in orange. These are updated in real time so they can check their progress. We see this kind of operational assistance as a key use case for machine augmentation, especially for pragmatic applications like using hybrid machines for prototyping or other research contexts. However, we are also interested in creative or even improvisational use of machines, which brings me to the final modality I have to show you today. Similar to the first module, this one shows possible future states, but it extrapolates further into the future. It matches the user's current knitting against a handful of designed heuristics to show paths that the user might go down and step-by-step instructions to get there. By making suggestions, we prune down what can otherwise be an overwhelming possibility space while leaving the outcome ultimately up to the user. We found that users did feel that the system was meaningfully interactive. While the user's trust relationships with the system were complex, especially when they reflected on their prior use of systems which were more automatic but less reliable, ultimately most of our users felt that they had control to some extent over their outcomes, that using our systems had elements of gaining mastery, even if they didn't always know exactly what was going on, and even that they felt that their outputs were enriched by involving hands-on labor. In other words, by revisiting an ostensibly antiquated manual machine and introducing lightweight technical augmentations, we produced a hybrid system which is both much less expensive than the fully automated version, as well as having potential for meaningful creative interaction with complex user experiences of ownership, trust, and mastery. We hope this inspires you to consider revisiting the vast breadth of not currently computational fabrication equipment that exists in the world in a wide variety of domains. Thank you for listening, and feel free to reach out to me via email, leah@cmu.edu, or Mastodon, leah@hci.social.